Hello, my name is Professor Johnson, and today we will be working with exponential distributions. Just as an intro, let's talk about the exponential. And exponential, usually our examples will be talking about time, okay? So usually over time. And we first need what's called the probability density function, our PDF, and that'll be f of x. This is represented by lambda e to the negative lambda x. Now lambda is our decay parameter. Some books use this Greek letter lambda, and instead other books use m, like a little m. Really it's just a placeholder. So we have lambda. Now lambda is important, and lambda will be 1 over mu. Mu is our mean, our average, and this will be extremely important. We always need to find this first, okay? So always find lambda after reading your example. Now, mu is also equivalent to sigma for the exponential distribution. It's just a special case, okay? Now, what I mean by decay parameter, if we draw a picture, we could see this visually. Now I'm going to start here at lambda, and it really decays down. It goes towards 0. So eventually over time it'll get very, very close to 0. It's what we call a horizontal asymptote. Now we're starting at a height right there of lambda, because if you plug in x of 0, e to anything, so if I take your calculator, if you use second ln, that brings up the e. E to the 0 is always 1. So then what you're left with is lambda. So that curve that we have right here is our f of x, and you see it's decaying. Now, what we really are interested in is area under the curve, probabilities. And probabilities come from what we call the Cdf. Okay, so we're going to need the Cdf. And the Cdf will represent our probability under the curve. So the probability that x, let's just say right here is b. We could mark a b right here. And this formula will always read to the left. So if we had probability that x is less than b, I'll keep it in black. Less than b is 1 minus e to the negative lambda. Now instead of x, we have b in this example. Okay, so you plug in that value of b, whatever you are interested in on that interval. Okay, this calculates that area under that curve right there that I just double shaded. Okay, always reads to the left. Now if you wanted to get the area up above b, you would have to do 1 minus all of everything that you've just written here, 1 minus e negative lambda b. Okay. Now, if you go on for time forever and ever and ever, like time out to 100 million minutes or 100 million hours, that area under the curve would truly be 1, totally. And you never think of negative time, so that's why I've stopped at x equals 0. I never went to the left here. Okay, I never went that way. Okay, let's do some examples. So imagine the wait time to be seen to set up your water utility account in a new county is exponentially distributed with an average wait time of 10 minutes. Okay, now first, you see how it says average wait time of 10 minutes? Mu is 10, right? Mu is 10, or 10 minutes, right? We also know that mu is equal to sigma. But like I said earlier, we need to find lambda first, and lambda is 1 over 10. So this is our decay parameter. This is showing us how we're decaying. Now, if you think of the picture, it's decaying like this. Okay, so you know 1/10 is right there. If you think about it, you're more likely to be seen earlier on than really, really late, okay? That's why it's exponential and you think of time, okay? So earlier on, you're more likely to be seen. Later on, it's less likely to occur. Okay, so if we think of this, let's look at number 1 now. Find the probability it takes less than 5 minutes to be seen. Okay, so if you imagine 5 is about there, less than 5 minutes. So we're looking at the probability that x is less than 5. This will be equal to, now we have to use our CDF formula. What we do is 1 minus e to the negative lambda. Now lambda is 1/10, so e to the negative 1/10. Write that a little bit better. Negative 1/10 is multiplied by that 5, because that's what we're interested in. Okay, so 1 minus e negative lambda times our x. Now, what I want to do, let's use our TI-84 calculator to calculate this. So over on the left, 1 minus, make sure you use subtraction there, and then you do second ln to bring up the e, but now you have negative 1/10. You want to use the negative right there. And really a different way to write negative 1/10 is, you see, I'll do this off to the side. Negative 1/10 could really be written as negative 5/10, because 5 could multiply by the 1 in the numerator. Really, 5 is truly over 1. So negative 5/10 is actually easier to write. So I'm going to put that in the calculator like that for you. Now, if we just take, 3 decimal places? Let's see, we would have 0.393. Okay, so 0.393. Okay, so that accommodates number 1, our first example. Now number 2, more than 5 minutes. So I'm going to change colors here. More than 5 minutes would be everything up above, right? Anything above 5. Probability that x is more than 5. Now we know that the area under the entire curve is 1. And we know the area underneath less than 5. So if we do 1 minus what we just did, 1 minus negative, really, 5/10, if we do 1 minus what we just did, we'll get everything else left over. So let me show that. 1 minus, now I'm using parentheses to subtract everything that you just did. 1 minus e negative 5/10, and then arrow over, close the parentheses. You get to 3 decimal places, 6, 0, and then that would round up to 7. Okay, so if we look at our picture, visually you can see that that little red shaded area is 0.393, and then this upper shaded area is 0.067. Now what do those add up together? Those add up together to be 1. So now you've accommodated for the area under the entire curve. Okay, so that represents a more than and a less than case. Okay, so continuing on, what if we have just at least 15 minutes to be seen? So first, we're still using the same example. So average wait time 10 minutes, that's lambda is 1/10. If you draw a quick sketch, at least 15 minutes. Okay, so 15, I'm going to mark there. Now, if you think about this being x and 15, you want to think about the inequality symbol. It's going to take at least 15, so not less than, but you're going to be greater or equal to 15. It has to be at least 15, so greater or equal to 15. So that tells me that the shading right there, I'll just shade that in, is everything above. And what we saw before in our last example, you'll find the probability, you do 1 minus, and really you subtract away all of this lower part, So you do 1 minus e. Negative lambda would be your 1/10, and 15 is the x in this case. Let me get a little bit more room there. Okay. And we saw before that you could really rewrite that as negative 15 over 10. So this would be 1 minus, parentheses 1 minus e to the negative 15 over 10. Now, if you know a little bit of algebra, you could actually make this a little bit nicer. You see how you have 1 and then you have a negative that could distribute? The 1 minus 1 really cancels away, and then the negative and the negative here would create a positive. So if you just put positive e to the negative 15 over 10, that'll be equivalent, and that'll be a little bit quicker to write. So I'll show both ways, but if you do this way, you'll get that, which is 0.223. Okay, so that'll be our solution, but also show you the original way that I started. 1 minus all of this would also give you the same answer. Okay, so if you distribute that negative, you could get the same answer as if you didn't distribute. No matter which way you do it, you'll get the same answer. Okay, now if I asked you what would the probability that x is less than 15, you'd be able to find that by doing 1 minus the 0.223. So if you did 1 minus 0.223, I know that really if you think of the probability, 0.777 is right there, and 0.223 is that upper region. So you have the lower and the upper. Both of those added together would give you an area of 1. Okay, and then let's do one more example where we're between values now. So let's recap. Lambda is a 1/10, and if we draw our picture, we're decaying, and it takes between 12 and 20 minutes. So let's mark 12 and 20 right there. I really should be putting arrows on all of it, but now find the probability takes between 12 and 20. So between would be that shaded part, this shaded region right there. Now, this one's a little bit different. Now imagine here's our probability notation, and I'm going to draw a couple more pictures. So we want to be between, so the x is between 12 and 20. So it's written a little bit different, but not too much different. Okay. If you think about it, we have 20 and 12. Now our formula always reads to the left. So if we take our small picture here and I mark 20, I could find the area all the way to the left by doing 1 minus e negative lambda times x. So that would be negative 20 over 10. And that would get everything to the left. Now I could also do that same thing, but only go up to 12, and I could do 1 minus e negative 12 over 10. Okay, you see right here I'm drawing two pictures truly, and there's really a difference of that little blue piece right here. So if you found all of that, if you find the 20 first, so if you do 1 minus e negative 20 over 10, you find that first, and then you subtract off the bottom piece, the 1 minus e negative 12 over 10, that smaller part. Okay, so if you take this part, which is the whole thing, and then you subtract off this next part right here, this next part is just that part, which is really represented here, and that is represented right here. If you take that difference, you see what's left over? It's just that little blue region. Okay? So really you're subtracting here. And you have to be careful with parentheses when you go to the calculator. 1 minus e negative 20 divided by 10. Arrow over, close the parentheses, subtract, start a new parentheses, 1 minus, and then e raised to the negative 12 over 10, and then you close the parentheses. When you hit enter, you got a value of 0.16. Now the 8 bumps up that, so 0.166. Okay, so we've rounded to 3 decimal places, we're done. Now this answer makes sense because we're between 0 and 1. All right. Thank you for watching the video.